Welcome to the Basic Skills series in physics. In first unit of this series, we'll learn how to visualize and calculate displacement. If you haven't watched that lesson yet, go ahead and check out the linked video first. Today, we are going to look at two common ways of visualizing motion diagrams and graphs. We'll use both methods to explore average velocity and instantaneous velocity. Let's start with the motion diagram. The dots you see here in this diagram shows the object's position at equal time interval. Emphasis being equal time interval. In this example, each dot is 1 second apart, but the interval could be anything, a tenth of a second, half a second, and so on. One can draw a displacement vector from motion diagram by connecting two consecutive dots. In this case, the delta x1 represents the displacement in first second. Similarly, the delta x2 represents the displacement in second. And we could keep drawing these arrows, but for briefness, what I'm doing is I'm skipping all those and coming back here. So what happened in this case? Object slowed down and then turned around and then started moving backward. So just like we denoted displacement in first second, similarly we can denote displacement in 13th second and 14th second and so on. This diagram has a lot of information, one being positions, and there are times. We can now draw a displacement, and since the time is fixed, the displacement vectors are proportional to the velocity as well. So we have velocity information, and it also has this information that how the velocities are changing. Isn't that awesome? And change in velocity gives us information about acceleration. We'll talk about acceleration in the next. Now let's talk about average velocity. So since we have displacement, we can find the average velocity using this formula. So in short, we denote velocity by lowercase v. And here I am writing subscript AB is for average. And average velocity is displacement divided by not just time, but time interval for that displacement. So for example, calculating the average velocity between 0 and 1 seconds, I can write displacement during that time interval divided by the time interval. And in this case, this time interval is exactly 1 second, but it could be any. Similarly, average velocity at, let's say, 14th second can be written as delta x 14th divided by time interval. And by the way, this is just a notation, and I'm using subscript in the displacement notation to indicate that these displacement, they are not same, they are changing with time. Okay, so that's what the subscript is. Otherwise, we used simply delta x for any general displacement. But here, by putting subscript, what I'm doing is I'm being more specific. For example, let's suppose in the first second, this object traveled 2 meters to the right. So that means I can write the average on the first second positive 2 meter divided by 1 second. I am assuming right as positive. And remember, this is assumptions. We could choose left as a positive. There is nothing wrong with that. Often we choose up as a positive and right as a positive, but could be any direction as a positive. So here, positive sign represents the direction of this displacement vector. So since we are assuming positive is right, I can also read that this as a 2 meters to the right. But since I cannot write the direction, physical direction in the equation, what I'm doing is I am replacing that with the positive sign. Okay, so that's the average velocity. So for example, over here, let's say at the 14th second, let's say this displacement was only 1 meter, then how would I write it now? Since it is pointing to the left, it's going to have negative sign now. And 1 meter, divide that by, and remember time interval is 1 second. Now, if I want to find the average velocity from all the way from 0 second to 14th second here, then what I do, I draw from initial point of interest, which is 0 second I'm saying, to the 14th second, which is final, for example. Final here, and initial here. For this particular example, is going to be the displacement. Okay. So now what's the average velocity then in this case? Up to 14th second, that is total average velocity. Okay, so that means it's going to be this displacement here. Let me just write delta x that. Okay, delta x divided by the whole time interval. So the displacement value, I said, okay, this was around 2 meters. So maybe this is 1.5 meter. I'm just throwing random number here, okay? So that means total would be 3.5 meter. And overall, it is still pointing to the right. So that means this is going to be positive displacement. And time interval in this case is going to be 14 seconds. Let's talk about speed. The speed is like a velocity, but in this case, we're not dividing displacement by time interval. Rather, we are dividing distance by time interval. What's the difference between distance and displacement? Distance is path length. So we need to count whole length. So for example, up to 14th second, the displacement was just the shortest distance between initial and final point. But for the distance, we have to go all the way here and then come back. So this is a lot larger. Okay. So I don't know. I can throw a number, but that number gonna be definitely way larger than 3.5 meters. So let's say this is, and for the speed, I'm not writing any positive or negative sign in front because speed is not a vector quantity, it's just a scalar. It does not have information about the direction. And time interval is 14 seconds. So this is 1 meter per second. And in this case, you can see the average velocity is way less than the average speed. As long as the object is changing direction, reversing direction like this, in that case, what happens? The value of average velocity and speed are not same, but they are same when object just keeps moving in just one direction. For example, up to 8 seconds in this example, what happens? Object just keeps moving to the right. So that means the distance and displacement, value of displacement and distance, they're going to be same. Means when we calculate average velocity and average speed, both values going to be same. And by the way, the speed I calculated is also average speed. Now let's talk about instantaneous velocity and instantaneous speed. So we learned that the average velocity is displacement divided by time interval. But if we look at the velocity at very small time interval, or not even an interval, when interval goes almost to zero, means it becomes very, 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 very small, that's the instant. So that is the instantaneous velocity. A familiar example is a car's speedometer. The number you see is both the speed and the magnitude of velocity at that instant. So the instantaneous speed and the instantaneous velocities always have the same value, unlike average velocity versus average speed. So there is that difference. Just keep that in mind. All right, let's take a look at this position versus time graph. Position is in meters and time is in second, and this line represents the graph. So from this type of graph, we can read off positions at different moments and use them to find displacement and then the average velocity. So let's take a look at an example. Let's suppose we want to find the average velocity between time 2 seconds and 5 seconds. And I am choosing these points here because they are easy to read, because corresponding point on the graph are exactly at those time. But the time if the time was, for example, 4 seconds, then that corresponding point would have been that one, and we would have to make guess. We can do that, but let's look at the convenient point. There are two different ways we can find the average velocity from position versus time graph. One, first find the displacement and then use that displacement and corresponding time interval to find average velocity by just dividing that displacement by the time interval. So let's do that. So to find displacement, what do we need? We need final position and initial position. So here 5 seconds is our final time. Let's write TF, and 2 seconds is initial time. So in this case, time interval is just 3 seconds. Now let's read the corresponding positions. So this is going to be initial position, and this is going to be our final position. It is positive 14 meters, and then initial position is also positive, but there is negative sign in the formula of displacement. So what are we going to do? We're going to multiply negative and positive. Result is negative, so that's why it's going to be negative 10 meters. So with that, we get positive 4 meters. Now, the average velocity being displacement over time interval, we can use these values we calculated for meter for the displacement, and we have time interval, corresponding time interval, 3 seconds. So that is around 1.3. So let's just leave it there, meter per second. That's the average velocity. Now, what's the another method? We can connect these 2 points on the graph. our point of interest by a straight line segment and find the slope of that. So for this, rise is this much and run is this much. So when we read this, we say, okay, that is run and this is rise. And looking at this graph, we know rise is exactly positive 4 meters and run is 3 seconds, just like before. Okay, so we are getting same numbers, means we are getting same velocity, average velocity, so no surprise there. As you can see, if I were to find, let's say, slope of, let's say, these two lines, their velocity going to be different. So velocity is changing here. Okay, so if I were to calculate instantaneous velocity, that would be different than this 1.3 meter per second. So that's why the instantaneous velocity and average velocities are not same. They may be same in only in some special occasion, that would be just purely coincidence, or when velocity is not changing at all. Otherwise, they are different. Now let's move from average velocity to something even more important, instantaneous velocity, or simply velocity. To find the instantaneous velocity at a specific moment, in this case, let's say at 3 seconds, we draw a tangent line to the position time graph right at that point. A tangent line is a line that just touches the curve at that one point. It's kind of tough to draw that because there can be several lines just passing through one point, but the tangent line cannot cross the curve. So to make it easier to begin with, what we can do is we can put another point right next to it towards the increasing time. So I'm putting another point right next to it. As close as possible is the better choice. Once we have these 2 points, we can draw a tangent line like that. Okay? So this line shouldn't be crossing or intersecting with the original curve. So now once we have drawn the tangent line, we can treat this as any straight line and find its slope. And slope of that tangent line at that point is the instantaneous velocity at time. So let's figure out the slope. So to find the slope, what we can do is we can choose 2 convenient points. So the way I have drawn here looks like there aren't very convenient points. Since the tangent line has to pass through this point, this could be one point that we can easily read. Now, which other point we should be choosing? Let's choose this one here. This is at 1 second. So that means now we need to find rise over run. So let me just make this triangle so that easily visible here. So this is going to be rise. This is going to be run. So calculating run is really easy because it goes from 1 to 3 seconds. Means the run is just 2 seconds. How about rise? So rise reaches to 12 meters. Run starts after 8 meters. So this is 10, so half would be 9. So this is like more like a 8.5. It's a best guess I'm making. Okay, so that means 8.5 to 12 is the rise. So that means it has to be 12 minus 8.5. It looks like that would be 3.5. Okay, and this is meters. So slope of tangent line is a rise over run, and the rise in this case is actually positive 3.4 meter, 5 meter, because up is positive, and this is rising, is going towards up, or positive 12 minus 8.5 is, this is positive 3.5, just from the calculation as well. And time interval, just like we said, is 2 seconds. So this ratio gives us, let's see, 217 second. So this is the instantaneous velocity at 3 seconds. Now here is something important to emphasize. The instantaneous speed is simply the magnitude of the instantaneous velocity. Since the speed has no direction, so this instantaneous speed is always the absolute value of the instantaneous velocity, which comes in handy if the velocity has a negative sign, right? So we just get rid of it. If the instantaneous velocity was, let's say, negative 1.7 meters per second, then the speed would still be 1.7 meter. Now let's summarize what we just learned. We learned about motion diagram, and we learned that a motion diagram shows an object's position at time interval using dots for the positions. Connecting the dots with the arrows shows the displacement, and those arrows are proportional to the velocity, average velocity. So another thing we learn about is the average velocity. Average velocity is defined as displacement over the time interval. It tells us how fast the object moved on average during that time interval. On a position versus time graph, average velocity is the slope of line connecting those 2 points. And remember, distance and displacement are not always same. They are same when object just keeps moving in the same direction. But if they turn around, then what happens? They are not same. So displacement simply looks at the change in position by looking at simply initial and final position, and it does not care what happens in between. However, the distance is the path length or the total path traveled. They are same only when the object does not change the direction, yes. So the instantaneous velocity is the object's velocity at that specific moment. On a position versus time graph, you find it by drawing a tangent line at that point. The slope of the tangent line gives the instantaneous velocity, and it also gives us the instantaneous speed.